All right, so this is going to be a quick explanation of the Unit 7 FR review. Again, highlighting some of the answers, why they are what they are, quick explanations. Again, the key is here, but just kind of talking through it as if you were kind of in class. So the first question is talking about the eggs being sold contaminated with salmonella. That's great. Can cause food poisoning in consumers. Large egg producer takes an SRS of 200 eggs. Remember, SRS, simple random sample. The lab reports that 9 of these eggs had salmonella. Unknown to the producer, 3% of all eggs shipped had salmonella. Identify those things. So population is, who is it that you're talking about? What are you talking about? Who's the population? Who's everybody? And we're talking about all of the eggs that are being shipped on this one day from the egg producer. That's who we're talking about, right? We want to know something about all the eggs, okay? Parameter, which also starts with P, defines a population. Remember, P for population, P for parameter. We didn't know, or was unknown to the producer, but we were told in the problem, 3% of all eggs shipped had salmonella. So 3% is a population proportion. It's a parameter. It's a number talking about the population. 3% of all eggs, right? Whereas a sample, which is the 200 eggs, a statistic, which again starts with S to define a sample, which starts with S. This statistic is a number that defines just a sample. So we had the 200 eggs, only 9 out of the 200, aka 4.5% or 0.045 of the sampled eggs have salmonella. So statistic is a number that defines a sample. A parameter is a number that defines a population. Population is everybody or all the households or all the eggs. A sample is just the smaller subset that you are selecting in that case. Gallup poll once asked a random sample of a bunch of adults, do you happen to jog? Suppose the true proportion of all adults who jog is P equals 0.15. Remembering P stands for population proportion. What's the mean and standard deviation of the sampling distribution of P hat? So P hat is sample proportion. Sampling distribution of P hat would be, if you took one sample, right, you'd have from 0% to 100%. If you took one sample, you'd get maybe a small percent saying, yes, I do the thing. Maybe another sample, maybe is a whole bunch of joggers in that group. Maybe it's a running club or something you happen to ask, whatever. Maybe you have a higher proportion. If you had all these sample proportions put together over trillions and trillions and trillions of possibilities, that creates the sampling distribution of P hat. Some will be on the lower end, some will be on the higher end. But what we do know is if you average them all together, you would get the population proportion, which is in this case 15%. So the mean of all of those sample P hats, right? The mean of all of those sample proportions, the mean of all of those possible trillions and trillions and trillions of possibilities actually always just equals the population proportion. So if you needed to know some unknown population proportion, you just need to take 17 trillion samples and then you'd figure it out. Obviously, that's not what we normally do, but that technically would be correct. Standard deviation, however, because we took a sample size other than 1, once we increase sample size, we know that sampling variability, aka standard deviation, goes down. So we need to use this equation, which is given to us on the formula sheet. However, in order to be able to do that, we need to check the 10% condition, which states that our sample size must be 10% or less of the population. We're talking about 1,540 adults. They don't tell us who we're asking, but we can kind of assume a large population of people, and even like a small city or a state or a county or a country. Obviously, 1,540 will be less than 10%, because as long as you have 15,000 adults in that area, you're good. So even a small city probably has at least that many adults. So because we did that, we're able to do the calculation here, and we get that the standard deviation is 0.009. Again, using the formula that is given to us on the formula sheet. Whereas in letter B, to determine whether all of these P hats eventually create a normal curve, we have to use the large counts condition, which is NP, N1 minus P greater than or equal to 10. Because both of those numbers end up being at least 10, remember that's 231 successes we expect and 1,309 failures out of the sample. Basically, people that say yes and people that say no to jogging. Because of that, the sampling distribution of P hat is approximately normal, right? So even though we only took one sample, we know that if in theory we did all of these samples, it would create a normal curve, and because it eventually would create a normal curve, we can apply normal curve ideologies together using our mean that we already figured out, using our standard deviation that we calculated. Obviously, you want to draw the normal curve using those numbers as reference. And then between 13% and 17%, that's a normal CDF question, but the lower bound, upper bound are given to you. Again, being careful to use the mean and standard deviation we're given, and it is pretty much almost 100%, obviously in this case 97.4% likelihood that you'll be somewhere in that range, right? Because the probability is so high, it's partly because the standard deviation was so low, right? So you're going 2 standard deviations above and below. That encompasses, more than 95% of the population. Next question here. We have birth weights of 400,000 newborns are analyzed. Supposedly, the distribution of birth weights is approximately normal. That's important to know. With a mean and standard deviation given. In this population, the range is 3417. So the heaviest baby and the lightest baby are 3,400 grams apart. They use software to select 500 SRSs of size 5, and in each time they calculated the range. So that's what these dots are, right? Each one of these dots is the individual range from 5 babies that were selected at random. They selected 5 babies at random, they weighed them. They took the smallest baby and the heaviest baby, and they found their range, and they put that dot on the graph, right? So this dot over here means there was 5 babies that they randomly picked that had a highest and lowest range weight of less than 250 grams difference, right? So those babies, all 5 of those babies were really kind of close together in terms of weight. Part A and B is to sketch the distributions. One of it is just birth weights in general. The second one is if you take a sample size of 5. So this is simply just doing a normal curve because they told us it was approximately normal. Going 1, 2, 3 standard deviations out using our original data. But the difference in letter B is because they take a sample size of 5. Again, when sample size goes up, variability, standard deviation goes down. You now have to use your standard deviation equation. I didn't write it here, but technically you should be checking the 10% condition. 5 babies is far less than 10% of the 400,000. So obviously, as you can see here, the standard deviation is cut more than half. Or less than half, I guess you could think of it, more than doubled, whatever, however you want to think of that. So this is the same problem, still the same mean, still averages 3668, but the standard deviation means that it goes much less out, right? So part B is much more compact together, whereas part A is much more widespread. Graphs look the same, probably just copied the graphs, but if you look at the numbers, going to the edges, it's far different. Letter C kind of asks what I already answered earlier with the highlighted dot that I have here, except now they want to know the highlighted dot on this side. That 2750 or approximately 2750 means they took 5 babies and again calculated the range between those 5. So it's basically the sample range from one of the samples of size 5. 5 babies out of the 500 SRS that they did. 5 babies collectively had a range of about 2750 grams, heaviest and lightest baby. Okay, so again, you got to think of each dot as a sample of 5 with that group's range. Letter D is sample range and unbiased estimator. So remember that the actual range was 3417. 3417 is like way over here. Every single one of these is lower than the actual range, meaning it is not an unbiased estimator. The 2 words unbiased and estimator have different meanings. First of all, unbiased means when you take a sampling distribution, if you get some sample data that's lower than the right answer and some sample data that's higher than the right answer, you are getting unbiased data, right? Some are lower, some are higher. In this case, the data is very biased because all of those sample ranges, as expected, are way less than what the real range is. The only way you can get the real actual range is if in your sample of 5, you only had the heaviest, or in that sample of 5, you had the heaviest and lightest baby in your 5. If you're picking 400,000 different babies, the likelihood of getting the heaviest and lightest baby in a small sample of 5 is very unlikely, and in this case, didn't happen. right? So this is biased because everything is underestimating the right answer, and it's not a good estimator because an estimator means that when you get higher and lower sample data, it's going to average out to the right answer. There's no way that the average of those 500 in the graph average out to the right answer because every one of them is clearly way less. Seems like the average might be like somewhere in the thousands here, right? Nowhere near the actual range. So this is a sample range is a very, very bad example for unbiased estimator. Okay. Letter E, explain how we could decrease the variability of the sampling distribution. So if we increased sample size, instead of asking or taking 5 babies' weights at a time, if we did N is maybe 500 babies at a time, this data is going to get much more compact. It's going to squeeze in. Now, it's still going to be lower than the actual range, because the only way you're going to get the actual range is if you did the heaviest baby and the lightest baby, although if you take a sample size of 500, you're more likely, not necessarily guaranteed, but more likely to get the heaviest and lightest baby in there. But you're going to get a wider array of data, right? In the 500, you're going to get some really, really light babies and some really, really heavy babies. So your sample ranges will still be less than the right answer, but this data will probably become closer to the real answer and be less variable. Okay, so the standard deviation will go down, it won't be as widespread, and it'll probably be closer to what it really should be, which is up towards the 3,400 number. Okay, next question, talking about travelers passing through. Let's see, what do they do? Each time they require a person to press a button, either a red or green bulb lights up. If the red light shows up, they'll be searched by customs. If a green light comes up, they don't get searched. Customs agents claim that the proportion of all travelers who will be stopped is 30%. So 30% of the time, a red light turns on, supposedly randomly. Hopefully no discrimination happening here, right? And that's what they're saying should happen. Supposedly. To test this claim, a concerned citizen watched a random sample of 100 travelers push the button. Only 20 got the red light. So she watched 100 people do this. 20 out of 100 got the light. Now, is it possible that the right answer actually is 30%? The light turns on 30% of the time, but only 20 out of 100 got the red light? Yes, that's possible. The question is, how likely is that to happen? So we need to find the probability that the proportion of travelers who got a red light as small or smaller than this. So 20 or less. Right? Because if you even got less than 20, that's even further evidence that maybe 30% is not the right answer, right? So we're testing to see the concerned citizens testing to see whether or not 30% is actually accurate. We only got 20 in our sample. If we got even less than 20, that'd be even further evidence saying that 30% is not accurate. So what do we need to know? We need to know that this is just one sample. Our p-hat was 20 out of 100, right? But if we kept doing this over and over and over, this sample happened to be less. We'd probably get some samples that were higher than 30%, right? Assuming 30% is true, it would bounce all over the place. The average of all those p-hats would would average back to the 30%. That's the reality, right? Assuming, again, 30% is true. Standard deviation would change because we're taking 100 people at a time, right? But remember, 10% condition needs to be checked. 100 travelers is definitely less than 10% of travelers in probably any airport on any given day. Okay, so it's good. So we now have a standard deviation we can use. We want to use a normal curve calculation, but in order to do that, we need to check large counts. NP, N1 minus P are both at least 10. So that means the sampling distribution is approximately normal. We can draw a letter curve with a 30% in the middle. That's our mean. That's what we expect them to average out to be. That's a population mean, population proportion in this case. And we want to know 20% or less, right? Our sample was 20% or less. So we do our normal curve calculation, we get 1.5%. Okay, so 1.5% of the time, given these conditions, you would get a 20 out of 100 or less getting the red light. And in letter B, it says, do we believe the customs claims, right? Custom agents claims. If something only happened 1.5% of the time, right? We probably would not be very confident in that result. So the probability is really low, meaning assuming 30% was true, our result of getting 20 out of 100, or even rarer than that, which was less likely to happen, that only happens 1.5% collectively of the time. So since that is so low, we're starting to maybe think that maybe the customs agent's claim about 30% is not true, because we saw it happen. We saw 20 out of 100. We saw 20% happen. And if it's so unlikely to get 20% or less to happen, given the 30% claim, maybe we start to disbelieve, not believe the 30% claim. Okay. Now, if it was a higher percentage, we'd be like, oh, okay, this happens every so often, 1 out of every 5 times. But 0.015 is very rare, right? Less than 2% of the time. So could we have still just been one of the 1.5% times getting 20? Yes. But because it happened and it's very unlikely to happen, we maybe don't believe what the customs agent claim is. We don't necessarily have proof, but we are starting to gather evidence as to why that might not be true. Next question, we got an IQ test for adults. The distribution is told to be approximately normal. You have a mean, you have a standard deviation. What's the probability that a randomly chosen individual, just one person, right? Simple, straightforward, normal CDF, no issue here, right? Should be plain and simple. We were told it's approximately normal. We're good to go, okay? For letter B, find the mean and standard deviation of the sampling distribution for 60 people. So now we're taking 60 people at a time, okay? So you could take 60 people, average their IQ test, and sometimes it's going to be higher, sometimes it's going to be lower than the average of 100, right? So what'll happen, though, is if you take those higher and lower averages and average them all together, it should equal the population mean. So that's true. The average of all of the sample means will eventually equal 100. But because we're taking a sample size of greater than 1, we know that the standard deviation needs to change, which means we need to check 10% condition. Our 60 adults is likely less than 10% of all people over 16 years of age that have done this thing, right? Because probably more than 600 people have done this, since we're talking about people over 16 years of age, right? That's a lot of people. So the 10% condition checks out, therefore we can calculate standard deviation. A lot of these problems are very similar. And then lastly, we're asking what's the probability? Because we know that the population is already approximately normal, we don't have to check CLT, so we already are good to go. We should still state that, though, right? Say that because we know the the population distribution is approximately normal, sampling distribution of X bar is approximately normal. Because of that, we use our mean that we now know and our standard deviation that we calculated to get a very small possibility of getting 105 or more. So it makes sense, right? It makes sense that if you only do one person at a time, we could just happen to find a really smart person, right? But if you do 60 people at a time, for them to average 105 or higher, there needs to be a higher amount of smart people in that group. And it's very unlikely, given the parameters of this problem, to find 60 people that go 105 or more, because you're going to find some people that, may be smart in their own way, right? But they don't do well on this test. So they're going to bring the average down. And even if you have a genius in there, you have some people that maybe aren't as smart, the average drops down, okay? Would your answers to A, B, or C be any different if we didn't know that the population was approximately normal? So C would still be the same, because 60 people is covered by CLT, central limit theorem, so C would still work. B doesn't have anything to do with the population being approximately normal, so B is unaffected. A would be wrong, though. We would not be able to do A. We would not be able to do a normal curve in letter A, because if we didn't know the population was approximately normal, A's sample size is just 1. That's not 30, right? So we can't do letter A unless we know that the population is approximately normal. C we can still do. Sample size at least 30, we're good. Gypsy moths, we are told that the distribution is strongly skewed, so definitely not approximately normal. We take an SRS of 50 traps. The average of 0.5 and a standard deviation of 0.7 are the number of moths that are trapped, right? So actually it's the number of moths in each trap. So there's about a half of a moth per trap. Obviously some have none, some have 1, some have 2, whatever. Explain why it's reasonable to use a normal curve, even though the data is strongly skewed. 50 traps at a time, 50 sample size is at least 30, so central limit theorem applies. So we're good there. estimate the probability of getting sample size of 50 traps to have at least 0.6 moths per death trap. The mean, just like we've talked about multiple times already in this video, the mean is what it is in the population of all those XBARs. The standard deviation does change only after checking the 10% condition, which we can assume that 50 traps is less than 10% of all the traps, since we're talking about an entire state, right? So we have now a standard deviation to use. Normality, we already talked about that because the sample size is at least 30. We're good. You draw your curve, you do the normal CDF, use again your new mean and standard deviation, you get your answer. So basically 15.6% chance that in this circumstance, if you take 50 traps at a time, you're going to get at least 0.6 moths per trap, given the parameters of this problem. Okay. In a recent month, the mean number of moths on an SRS of 50 was exactly that 0.6 that we just talked about. Based on the result, should they be worried about the moth population getting larger? So if the moth population is getting larger, we would expect an increase of moths per trap, right? It kind of makes sense that there's more moths flying around. We see in this last problem that we expect this to happen about 15.6% of the time, right? So we don't necessarily think like there's a worry here because this happens, right? The mean number of moths, like it happens almost 1 out of every 5 times. 15.6% is almost 1 out of every 5 times. That's a lot higher probability compared to the last problem, which was only wherever it was 1.5% that we talked about here, right? That was only 1.5% of the time that happened. We don't believe the claim because it only happens 1.5% of the time. In this case, it happens almost 1 out of every 5 times, almost 20% of the time. So we may be thinking that like, oh, okay, like this seems to happen pretty regularly, even though 15% of the time is not often. It's not 100%. It's not even majority of the time. 15% of the time is often enough to believe, okay, this is probably one of those cases. We'll talk about this more in the future, but we've talked about it a little bit, but in future units, 5% is usually the magic number. Something happens more than 5% of the time, it's often enough for us to think it's believable. If it happens less than 5% of the time, then probably something went awry. Hopefully this